So last week, we introduced you the stack ADT and also the queue ADT. You should really know about the subtle differences that are actually fundamental for us to distinguish between the two data structures. They're quite similar, but they are not really the same. So namely, you want to know what's really the level versus FIVO property. If you're not too sure what I'm talking about, level versus FIVO, then you may just want to review the lecture materials more carefully from last week. And for this week, I would like to, first of all, start by finishing off the remaining two topics about the queue ADT. Namely, I want to talk about how we can implement the queue ADT using a circular array to really resolve one of the issues we actually identify in the fixed size array. That's something I would like to talk about. And number two, I would like to talk about another kind of interesting variance of the array. So here we talk about circular array. I'm also going to talk about the so-called dynamic array, which will also resolve one of the limitations for fixed size array based queue implementation. So these are the two things I would like to do first, and then we'll move on to more intermediate examples on recursion. That'll be the plan for this week. If time permitted, we'll definitely try to talk about the tree structure as well. Just mainly some gentle introduction. And then from next week, we definitely will move on to the tree ADT. Alright, so let's now talk about what a circular array is. The best way to learn about this variance of the fixed array is to use examples, which I'm going to do for sure with some different steps to illustrate different properties for the circular array. But before that, I would like to just go over some bullet points and show to you what you can really study after the example illustration. Let's now start with the bullet points. And so we want to maintain two numerical indices, f and also r over here. However, for the r over here, don't get confused with the r integer when we actually did the fixed array implementation. The r here and the r over there are not exactly the same. That's something I would like to point out right away, right? You can definitely see what exactly the r really meant in that fixed array implementation, which we spoke about last week, right? And so f should really point to, well, you can think about conceptually the integer index is really pointing to where the front of the queue is. Of course, if the queue is simply empty, it shouldn't really be access to the array. And also r is going to be the next available slot rather than pointing to the last element in the queue. That's something we'll see for sure. And this is the first property I would like to mention. In the case of the circular array, we're going to have some compromise because you will see that the main issue that we really want to address using the circular array is to make sure the dequeue operation is no longer going to take linear time, as in the case for the fixed size array. I'm going to brush up your memory by bringing to the corresponding page in just one moment. And however, there's one compromise in terms of the space. If you have, let's say, a fixed size array, well, just don't get me wrong. In the case of the circular array, the size will still be fixed. We still don't have any ability to really resize dynamically. That's not the topic for circular array. When we get to the dynamic array later, we will be able to actually change the nature about the fixed size. But for the circular array, the size will still be fixed. By just that, the way we actually manipulated f and r can allow us some flexibility that which will turn out to be more efficient than the conventional use of the fixed size array. That's something I'd like to note right away. You definitely want to make a note to make sure if I later on ask you to really compare, number one, the conventional fixed size array, number two, the circular array, and number three, the dynamic array, you should really know how to distinguish between these three. And let's say the size of the array that we have chosen is simply capital N, let's say. In that case, we're going to reserve one slot over there without storing anything meaningful. So this will be very important for us to really distinguish between the cases of empty queue and also full queue, the queue that's actually already filled out, right? That's something I will show you as well. And so this will be simply the length of the data array, right? Let me brush up your memory very quickly by drawing the connection to what we said last week. Remember, let me just make it slightly bigger over here. Remember, array queue implements the queue interface, and after you study about the circular array, one exercise I would like you to do, which is quite critical, is to create one class yourself called circular array queue, generic, and also implements the same queue interface, and then try to implement the various queue operations using the circular array based on what I show to you in this current video. I think that should be enough for you to actually get started. And I would say that's a very critical exercise for you to do. Just get prepared if I ask you any questions related to circular array in the future assessment. Let's recall very quickly about the fixed size array over here. You can see we declare some constant maximum capacity, and also we got some data array. And for the circular array, we're going to do something very similar. We're still going to have maximum capacity. We're still going to have the data array that's going to be fixed sized, right? Over here. However, the main method or operation we want to drastically improve is the dequeue operation over here, the dequeue method. If you recall, if we simply use the fixed size conventional array, whenever you actually dequeue, that means you have to shift the entire block of elements starting from the second elements until the end of the queue, and shift every element to the left by one position. That's what we had to do, right? In order to make sure we can actually always refer to data at index 0 as the front of the queue, right? That's actually the compromise we had to do. So that's why we had some not so efficient operation for the dequeue, for the fixed size array, the conventional one, which will be linear, right? That's something we learned from last week. And by using the circular array, by manipulating the F and R, which I just mentioned in the slides, in the circular array, we allow the flexibility such that the dequeue will actually be more efficient rather than just linear. That's something we'll see. All right, so that's something I'd like to draw the connection between the conventional versus the circular fixed size array. Alrighty, so let's now go back to the slides, and then I'd like to just go over a few more bullet points before I go back to the iPad to show you examples. And we talk about different cases. I'm going to talk about all the, I try to summarize all the information you should need. Of course, don't try to just memorize them. I think that wouldn't lead you a long way. You definitely want to understand exactly why we're using the different inequality or equality to decide whether the queue might be empty, the queue might be full, or maybe how we calculate the size of the queue, right? So these are everything that I'm going to try to illustrate using example on my iPad. We'll do it together, but this is some summary page that you can study by yourself, right? Of course, this is completely general about simply using the arbitrary value of R and also the arbitrary value of F, right? And then you're gonna use some, you're gonna do different expression checks and also different calculation to really calculate, for example, the size of the queue, right? That's something I'll leave to you to study on your own. But let's now go over one example together, okay? And what we want to really illustrate to you is we have some data array over here. Again, it's fixed sized, right? It's very important to really still not to lose the big picture. So when we talk about circular array, it is not dynamic, right? What? It's not dynamic in its sizes. So number one, it's fixed sized. Fixed sized. And also, okay, actually, let me just write it properly. Fixed sized. And no resizing is actually enabled for dynamic array. But we talk about dynamic array, which will resize by itself later in the next video or the next part of the lecture. Okay, that's number one. And however, number two, it will be flexible enough. Let me just draw the conclusion to you right away. It's flexible for performing operations like dequeue, right? Dequeue over here. All right, so these are the two main points you would like to take away after the example. Let's now just do it together, okay? And how do we initialize the empty queue, right? Empty queue means the data array simply store nothing over here, right? And the way we represent the empty queue is for F and also R, they will simply just be pointing to just at index 0 at the same time, just to begin with, right? So this will be F over here, and this will be R over here. They simply point to, conceptually, they're pointing to the same slot, F and R. Of course, programmatically, what you have to do to initialize the empty queue is you're going to say F initialized to be 0 and also R initialized to be 0, right? Also, intuitively, you can think about since R is really meant to point to the next available slot for the next item that's in queue to the queue. if R is pointing to 0, that means we haven't got any item in queue to the queue yet. So that's why the next one to be stored into the queue will be index 0. That's another way to think about why we will actually choose R to be pointing to 0 in the beginning. And F here is just to make sure we point to the same slot as R so that we can decide what the empty queue is. So what will be the condition under which we can decide the queue is actually empty? So this is a very simple formula over here. I'll write it down over here. So here, empty queue. Whether or not the queue is actually empty, you will just check to see whether or not R is equal to F. And initially, you can see 0 is equal to 0. So that's definitely empty, right? All right, so that's about phase number 1. And for phase number 2, we're going to try to enqueue 3 elements. And for the subsequent phases, we just try to interleave the operations of enqueue and dequeue just to see how the indices of F and R will actually change. You might be thinking, since R is supposed to point to the next available slot for storing the next item to be enqueued to the queue, R surely should be larger than or equal to F. However, since the queue is circular in its nature, or the array that we're actually using is circular in its nature, so that means it's not necessarily the case. So later on, you might see a situation like this. You might see that R actually comes before F. Right? So these are the cases that might also happen in the circular array. So those are the cases you have to be very careful, right? But I already gave you the general pattern and formula over here on the slides, and all you got to do is to follow the example and make sure you can program in Java on your own. I think that will be the complete exercise I would like you to do to complete your learning. Alrighty, let's now go back to phase number 1. So the starting state for the phase number 1 should be the ending state for phase number 0. So let me just copy this part over here so we can simply just reuse it. You can also see more explicitly about how the array is supposed to be progressing. Let me copy that and also paste it over here. And of course, let me just put F and R over here. F and R. Alright, so we started the queue being empty. F and R have been set up already. What we want to do is we want to actually enqueue for 3 elements in queue over here. But how exactly do we do enqueue? I'm going to give you some potential solution that may not necessarily work always, but that's good enough for now, right? So let me just move this a little bit down to just make a little bit more space for us, okay? So for enqueue, apparently what you're going to do is, because R is actually pointing to where the next enqueue item should really go, right? So we should definitely say data. Let me use the color, blue color here. So we should definitely say data at index R should be assigned to whatever item that you're trying to enqueue into, right? Just an item. You can assume item maybe just the argument or the parameter of the enqueue method. And also after that, we should really increment R to make sure the next available slot to really enqueue the next item, right? We want to update R as well. So R++. However, I'm just going to highlight this R++. It will work for this scenario over here, but does it work always? That's something you can think about, think ahead, but we're going to see that. Okay. So let's now try to do this. Let's say the first item we want to enqueue will be Alan. So I'm just going to put Alan over here without in a quote, but you can assume maybe just a string, a queue storing strings. Right, so I'm going to assign Alan to wherever R is pointing to, and also I'm going to say R++. So that means R is going to move 1 position to the right, right? That's the first enqueue. Straightforward. And let's say we do the second one. So we want to do 3 in total. And then wherever R is pointing to, which is index 1, we're going to store the second enqueue item, let's say Mark. And then we're also going to R++, right? Like that. And let's do one more. After that, I want to enqueue the third item, let's say Tom. And after this, I'm again going to move R to the right by 1 position, right? At the moment, as you can see, the number of elements we have is exactly the size of the array, -1. If you remember what I mentioned over there, the maximum size should be n-1, right? Over here, right? So you definitely can simply just do the following. Of course, you can maintain some size counter if you like, but we can actually calculate the size of the queue using just F and R. So how exactly do we do that? So let me just write it down. So the size of the queue, we have the following formula. Okay. Actually, before I get to the size, let's see how we can decide whether or not the queue is actually full. And apparently it's not empty, because you can see R and F, according to this formula over here, is not empty. What about the queue being full? So over here I can say Q is a full. Alright, is it? Okay, so the way to do it is, we want to say if somehow the next available slot to really store the queue, well, thinking this way, if this is the only empty slot in the array, if that's the only one, that will match the n-1 criterion that we spoke about in the slides. If this is the only empty slot in the queue, in that case, the queue is already full. And alternatively, we can think about if I try to go to the next slot that R is pointing to. If I can reach F, of course, if you only talk about the conventional sense of the array, if you say R goes to the going to the next slot, in that case, it should be index 4, but it's not valid. So that's why the circular nature is so important. If you think about R, I want to go to the next slot, I will go circularly if needed. In that case, I will actually go to F over here. In that case, if it happens to be wherever F is pointing to, so that means I got exactly one empty slot in the array, right? So this is really the condition for whether or not Q is full. Let me write down the formula, and I'll write down the inside as well. Right? So basically, you want to say R plus 1. However, R plus 1 may not be always the valid index. So that's why you want to do some modulo operation, right? Which you learned from the earlier Java course, right? This is a modulo operator. And I assume you learned about this operator from the first year of the Java course. If you got any trouble understanding or using the modulo operator, you can reach out to me. But for now, I'm going to assume you know how to do it, right? So I can say modulo the size of the queue, the size of the array, rather. The size of the array, which is n, right? What about in our case specifically? So in our case, you can see R over here is actually 3, right? R is 3. And F is actually 0, right? So actually, let me just write it down. So this expression over here should be exactly equal to F. So this is the Boolean condition you want to watch out for, right? R plus 1 modulo n equals F, right? If that Boolean condition is true, that means the queue is full. Is it the case for us? And 3 plus 1 would be 4, right? 3 plus 1 would be 4. Modulo, what's the size of the array? The length. 1, 2, 3, 4. So modulo 4 in our case, right? Over here. So 4 modulo 4 will just be 0. 0 is equal to exactly F over here, right? So that's why the queue is actually full. All right. This formula is so important because it really represents the following scenario, right? Let me just write down over here. When I say queue is full, so that means where R points to is the only empty slot of the array, right? So that's why if you try to go to the next one circularly, you can simply see F over here, right? Alrighty, so hopefully so far so good. And again, the reason that we want to use the modulo operator is actually exactly for such scenario, because when R plus 1 is actually larger than or equal to the size of the array, in that case, it will be invalid index. In that case, we should definitely try to make it circular by using the modulo operator. So you can think about in computer science or in software engineering, whenever you want to solve any problem by using some circular subroutine, in that case, most likely you have to use the modulo operator being your friend. All right. Alrighty, so let's see what else to actually talk about. What about the size of the queue, right? The size. Let's now talk about the formula for the size. The size of the formula, the size of the queue over here, and you can see here we got the situation where R is actually larger than F. This will be one case to handle, which will be quite easy, right? And one way to think about it is you can think about R Actually, well, first of all, we know that this is the case where R is actually strictly larger than F. This is one case. We'll see the other case a little bit later, right? Oh, by the way, this is like a second case. The first case was when R is exactly equal to F. In that case, it will just be empty Q, right? The size will just be 0. What if R is actually larger than F? The size when R is larger than F, how do we calculate it, right? Basically, what you would do is think about whatever R is actually pointing to over here tells you how many elements have been already stored in the queue or in the array. Because you can see R is pointing to 3, that means we got 1, 2, and 3. 3 elements in the array, right? However, F over here may not necessarily always pointing to 0. F could be pointing to 1 over here. Let me just give you that example there, right? It's really important for you to see how the general formula should be derived rather than just specific to the examples that we're talking about. Let's say somehow we got F over here, right? Let's say this is F. You can think about, let's say this is F. We got some element being stored over here, and then we got R. Okay, you can think about this is R minus 1. So that'll be the last item, and this is R, right? So this is R over here, and also you got more elements in the queue, right? So now what will be the size of the queue? The size of the queue should really consider these blocks, this particular block over here, right? This one here, over here, the orange one I'm highlighting over here. So how do we actually tell the size? So the way to think about it is R over here tells you about how many items, number of items before this index. Just for example, if this happened to be, let's say, 10 over here, in that case, we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got actually 10 elements at 10 slots before this particular R, right? Oh, so 10 before this R over here, right? That's R. And what about F? F would be very similar. F is really talking about, more specifically, how many empty slots before F. Okay, so this one will be number of empty slots. Number of empty slots before this particular index, right? So I would like to just maybe change the wording slightly over here so you can actually see very clearly about how to argue about it. So number of slots, right? So this really confirms about the meaning for R. Whenever I see the index for R, let's say 10, that tells me I got from index 0 to index 9, I got 10 slots before this index. And for F over here, let's say it's simply 3. Okay, let's say 3 over here. And 3 tells me that I got 3 empty slots before this particular index because I got 0, 1, and 2. All of them should be not part of the queue because the queue only starts from over here, right? So now what will be the size? So that will be exactly between 3 and 10, right? Between 3 and 10 over here. And exactly what's really between 3 and 10, you can definitely do some little bit math over here. So we are really talking about the inclusive interval between F and also R minus 1. Right? You can see only up to, but and also including R minus 1, but excluding R. So we talk about how to calculate how many numbers are there in this interval. It will be R minus 1 minus F plus 1. Okay? Minus 1 plus 1 cancel out, which will be equal to R minus F. So this is the ultimate formula. Right? I'm just trying to derive the formula together with you. All right? So the size would just be R minus F. Right? So far we have seen two formulas. One is about whether or not, well, actually we're seeing three formulas. One is about whether or not the queue is actually empty. The second one, whether or not the queue is actually full. And the third one is when R is larger than F, what the size will be for the queue. Right? So these are the three formulas we have illustrated to you so far. Right? Make sure you understand what we have got so far. Right? Let's now move on to phase number 2.